it is possible that what I'm going to say today in this video could be a bit controversial, because there are all these companies doing vector search databases or vector search capabilities in their databases, like I'm doing myself. No, this is the code of my vector sets for Redis. But everybody is obsessed with the recall performances. And if you test different kinds of quantizations with the usual benchmarks for vector similarity performances, which is recall over certain dataset, you will find that basically binary quantization is almost useless, while instead it's not useless at all, and I will show it in this video. But let's go backward and talk a few minutes about what quantization is and what binary quantization is. So basically, your vectors normally are a bunch of floating point numbers that identify some space. The problem is, one, FP32 floats are 4 bytes each. This is a lot of memory. Even just 300 components will result in 1200 bytes for each vector, and this should be also summed to many other things. For example, if you use for your vector similarity the data structure that almost everybody is using, which is HNSW, you have the edges that are fat pointers. You have a lot of you have the layers, different layers. You have a lot of overhead. So this is going to be summed to already quite big nodes, and it becomes a problem. But there is potentially even a bigger problem, which is about speed, because in similarity is costly to compute, especially from the point of view of memory bandwidth, because if you have so big vectors to compare, a lot of time is needed. So in order to reduce both space and time, what we do usually is to use quantization. For example, Redis Vector Sets by default use 1 byte quantization, so 8-bit quantization. Basically, you have a given vector that can have certain values, and you have a min and max value, and you get the absolute value, the maximum absolute value of all the components, and then you have a range from minus max to max, and you split this range in 256 steps in the case of 8-bit quantization, and so your vector is going to be an integer 8-bit type of positive and negative components. So your vector is still your quantization is still zero-centered in this case. That's great, and we go from 4 bytes for component to 1 byte, which is already great. It's also much faster, more or less 3 times faster or something like that. But what if we want to go more extreme than that and use binary quantization? In binary quantization, what to do is that the positive components are just set to 1. You use just 1 bit for each component, and negative or 0 components are set to 0. So basically, while in the cosine similarity you understand if the the two vectors represented by that represent your embedding space are facing more or less in the same direction, here you just check that each individual component is facing the same direction, or if is facing a bit more the opposite direction, and it becomes like comparing two images. Basically, you get this 0 and 1, it's like a bitmap, and at this point the Gaussian similarity becomes just the XOR between the two vectors, and then the Hamming distance between of this XOR. Let's see why. So basically, you have these two vectors, and you count how many bits are different. This is different, this is different, this is different, this is different, this is different. These two are the same. So these two vectors are quite different, and then you get the amount of different bits, 1, 2, 3, 4, 5, 6, 7, 8, 9, and you divide for the total number of bits that you have. So in this case, the similarity will, the distance will be something like 0.8. If we have only, if the vector will be identical, we will have 0 divided by 11, and it's 0, and instead, so the distance will be 0, and instead, if all the bits are different, we have a distance equal to 1. So you can imagine your learned embeddings that are represented via vectors, like black and white squares. For example, if you have components, so if you have a dimensionality of 300 for each vector, you can imagine a square of 18 by 18 in order to make space for all the components, since it's not a perfect square. And you can see certain pixels are on and certain pixels are off, and you want to see how similar are these two images. This is an incredible speed up, and also we go from 32 bits for component to 1 bit for component, which is 32 times less memory. So it's fast and it works great. However, normally, in order to benchmark how well vector databases are working, people use a test which is called the recall test. What happens is that you have some data set which contains vectors, and then you query these vectors in order to get them more similar to a given query, and you compare the results you get from your database to the ground truth. That is, if you scan each item and perform the similarity, which are the two most similar using full precision and using not HNSW but just a full scan, so you don't miss any, you don't have any local minima, because the HNSW algorithm is a greedy algorithm that provides you with an approximation of the top k elements. It's not like the perfect thing. However, this kind of the recall test itself, it's good, it's useful. However, there is a big but here. To start, even if the recall is not perfect, you get 50% of the recall, you have to check what instead of the nearest thing, what you got. Because oftentimes, from the point of view of the application needs, the elements that are misplaced are not really worse compared to what you really wanted, because there are embedding spaces where there are, many items that are extremely near. So if for a matter of precision, one is ranked before or after and is not in our top 10 results, it doesn't mean that the other results are useless. But there is much worse than that. For example, many people use this glove 100 test, which is basically word embeddings that are very dense and are very low dimensionality. Just 100 components. So let's go back to this idea that we have kind of a bitmap. As you can guess, if you have just a very small bitmap, like 2 by 2, almost all the embeddings will look the same, because there are very few potential possibilities about what can be on and what can be off. But instead, if you have 100, you have more, but state-of-art embedding models output larger vectors, like 1000 components or alike. Moreover, glove embeddings tend to be extremely uniform in the space. There is no enough clustering, enough separation between concepts. This is a characteristic that makes glove very a very hard test. So, for example, I will show you something. No, sorry. Let's execute this recall test. Okay, here I'm getting 92% recall on the average, which is very good. And let's check what I'm doing here. I'm checking the full precision embeddings, because vector sets support full precision in the rate, so 8-bit quantization and binary quantization. And I'm using an effort of 500 in order to search greedy in a broader way. And yeah, I get this result. If I do 100 times, basically, if I check the top 100 items instead of the top 10, I will discover that 86% are exactly of the ground truth and the other are not. Of course, I can change this result by exploring more. For example, if I explore more, that's 90% and so forth. And if I explore less, it's much faster, but it's 68 recall. Now let's check if I use binary quantization. I have this other key, which is binary quantized. The recall is 60%, which is very low, 70%. So this makes we think that, using a standard test, which is, what everybody is using, binary quantization is totally trash. But as I said, glove is a special case of embeddings which are extremely dense. There is not enough division. They are low dimensionality. They have all the kind of issues that prevent us to really understanding how things are working. Instead, I did something different. I added movies in these two keys. One is binary quantized and one is not quantized at all. So floating point 32 bits. Basically, I took the plot from IMDb and I associated, I take the embedding of the plot using a state-of-art embedding model, MX-Bay embed, large, and then I insert it. So now I can do, for example, give me all the elements which are similar here in the not quantized key to the element the matrix. And I get the matrix revolution, reloaded, avatar, forbidden planet, blah blah. If I test this with binary quantization, as you can see, the output is quite good as well. I have a recall of something like 50%. So we have all the truly near items are here, you know. And then I have the Omega code, which is here. The Forbidden Planet, which is here. The Avatar, which is here. And we are already are 60% recall, 70% recall. Okay, you got it. Also, explain me how, for example, I don't know, this item is really less relevant this item. Sure, mathematically the distance is greater. I can also show Redis to give me the distances here, both in the binary case and in the no quantization case. As you can see here, there are much more items that have exactly the same score, because there are the same number of bits that are you know, equal or different. And here instead I can exploit the full precision, but still there are many items that are pretty much very near from the point of view of the score. So even if mathematically they are different, it's possible that for my application these choices are also good enough. So basically what I'm saying here is that binary quantization works much better in real world use cases compared than how it works in certain benchmarks. Okay. So this is my distance function for quantization, no quantization, 8-bit quantization, binary quantization. Let's see how simple it is. I have to optimize this a bit using, for example, 2 accumulators in order to speed up it even more, but it's already very fast. So vectors, distance binary, just we get the number of full words that we have, and then we count the opposite vectors here, and then we do the opposite vector 2 times. Why 2 times? Because normally with cosine similarity I have a score from -1 to 2 that I normalize to have the distance from 0 to 2, and I want it to be the same, to report the same quantity, whatever the quantization is. Also, okay, I want also to show you something else. Yeah, Redis benchmark query. For example, this is the full precision benchmark. Okay, let's just take this part. And here I'm getting it was 37k operations per second, which are already a lot, by the way. Let's test with binary quantized vectors, and it's a lot faster. My cold is killing me. Never go to conferences, there are all the kind of bugs. Fuck. So it's faster. Also from the point of view of the memory usage that we get, even if this is an approximation, but wow, that's huge. The difference is very big. Basically, we are using like 6 times less memory in order to store the same data. Okay, so binary quantization is great. Binary quantization is one of the features of vector sets. By the way, when I use full precision versus integer 8-bit quantization, I see no difference in benchmarks, in most benchmarks. Basically it's the same, so there are no very good reasons to use no quant FP32 vectors, but I believe the choice is actually between 8-bit quantization, 1-bit quantization, depending on the application. Bye.